In this video, we're going to look on axial loaded members, and another session, we're going to look on statistical indeterminate structures. The steel tube is fitted around a solid aluminum cylinder as shown below. So this is the diagram they're talking about. The assembly is compressed between rigid cover plates by central applied forces. The aluminum cylinder is 70 millimeters in diameter, and the steel tube has an inside diameter of 80 millimeters and outside diameter of 100 millimeters. If the force which is being applied is 240 kilonewtons, you want to find the stress set up in the steel tube and in the aluminum cylinder, and after that we're going to find the change in length of the assembly, meaning of the wall section. Okay, so meaning of the wall structure. Okay, so what we're going to do first of all, we're going to start by drawing a free body diagram. Okay, so from here, what is going to happen? We know that this is a tube and it is being compressed, so I've drawn. So I'm going to have the force which is F 240 newtons, the force which is being applied, which is 240 kilonewtons. This force, we're going to have a reaction inside. So this is going to be the reaction which is going to opposite, since it's rigid, meaning it is not going to move. So there's going to be an opposing force, which is going to be the reaction right here. Okay, then the other thing that I've done, I want to look at the cross-sectional more stress we're looking at. So we're going to cut this and we're going to look at the cross-section. And the other thing that I've done was to draw the cross-sectional area of the cross-sectional view of this thing. So we have this, the bigger circle, and we have 1, 2, 3 circles. So this is the section for the steel, and this is the section for the aluminum, and inside is a tube, but there's nothing. And these are the diameter we've given of the outside diameter of the steel and the inside diameter of the steel, and also the diameter of the aluminum. So first of all, what we're going to do, we're going to write the given data, which is going to be the numerical data. So I'm going to write it here, which is the force is 240 kilonewtons, and we're also given the modulus of elasticity. So this is ES for steel and this is EA for aluminum. So let me just write ES here for steel, which is going to be 210 gigapascal. EA for aluminum, which is going to be 70 gigapascal. The outside diameter of the steel is 100 and the inside is 80. So I'm going to write GS1 for the inside diameter of the steel. I'm going to write it as 80 millimeters, and GS2 is the outside diameter. I'm going to write it as 100 millimeters. And after that, I'm going to look on GA2, the outside diameter of the steel, of the aluminum, which is going to be 80. So it's going to be 80 millimeters. And I'm going to look on GA1, which is going to be the inside diameter of the aluminum, which is going to be 70 millimeters. Okay, so this is the information that we're going to need, and we're also going to need the area, since we're going to look on stress, and we know that stress is equal to the force applied over the cross-sectional area. This is the normal force that we're talking about. So let's look at the area of the steel. So know that the area of the cross-sectional area, or the area of a circle, is equal to pi radius squared, or pi over 4 times the square of diameter. So we're going to say pi over 4, and we have two diameters, the outer and the inner. So I'm going to write d2 minus d1 squared. That is going to be the area, and we know it's going to be pi over 4 for d1. This one is s, right, for steel. So I'm going to write ds2 and ds1. So I'm going to say 100 minus 20 squared, and we're going to see that the area of the steel is going to be 100 pi millimeter squared. And if we move on to the area of the aluminum, it's going to be pi d2a minus d a1, and we're going to square that, and that's going to be pi over 4. And we say the outside is 80 minus 70 millimeters squared, and we're going to see that that's going to be 25 pi millimeters squared. So we know that the assembly is static, which means it's not moving. So I'm going to write the equilibrium equation right here. So what I'm going to do, I'm just going to take the right section. I'm going to take the right section of this assembly. So what is going to happen? We're going to have the reaction of the force, direction of the steel, and direction of the copper. So let me write it. R is equals to the force the reaction force of the aluminium plus the reaction force of the steel. There's no copper, just steel and aluminium. That means F1, Fa for aluminium plus Fs, which is the force of the steel, minus the opposing force, which is the applied force, the compressive force, minus F, that should give us 0. So we can say Fa plus Fs, and that should give us this force, F, the applied force, and we can call this equation 1. But since we have two unknowns and one equation to solve this one, and that equation is going to be the equation of compatibility. So let me write the equation of the compatibility right here. So in the equation of the compatibility, we know that the change in length of the steel and the change in length of the aluminium is going to be the same. So I'm going to call this the second equation. And also need another equation here that is going to be the force displacement relation. So on the force displacement relation, you know that the change in length of the steel is going to be the force applied, and that force is going to be Fs times the length, which is going to be Ls divided by area, the area of the steel, times the modulus of elasticity of the steel, or Young modulus of the steel. And I'm going to call this equation number 3. Then the displacement of aluminium is going to be the force applied to the aluminium is going to be Fa times the length, La times the cross-sectional area, Aa times the Young modulus Ea, and that is going to be the fourth equation. And that means here we needed L. I'm going to write L is going to be 200 millimeters. You know that La is equal to Ls. So now we have enough equations to solve our problem. So I'm going to sub 4 and 3 into equation number 2. And from here, we have said that 3 should be equal to 4 from here. So I'm going to write Fs, Ls here, As, Es here, and I'm going to write Fa, La, Aa, Ea. Now I'm going to make either Fs or Fa subject of the formula Fs, but we said La is equal to Ls, so you can just divide both sides by Ls. So that means Fs is going to be, if you multiply both sides by As and Es, it's going to be Fa times Es and As divided by Aa and Ea. So this is the formula that we have, and I'm going to call it equation number 5. Okay, so now let's look. We have to remember that the Young modulus is in Pascal. That means that is going to be Newton per square meters, and our diameter or area in terms of millimeters. And we know that 1 millimeter is equal to 1 times 10 to the power negative 3 meters. Meaning, if say 1 millimeter squared, we're just going to square this one, and we're going to get 1 times 10 to the power negative 6 meters squared. Okay, so let's do that. So I'm going to have Fa right here, and we have Es, the Young modulus of the steel, which is right here, is 210 times 10 to the power 9 Newton per square meter, times area. What is going to be the area? So the area of the steel is 100 pi times 10 to the power negative 6 meters. We have changed it from millimeters squared to meters, and we're going to divide this by the area of the aluminium. So the area of the aluminium is going to be 25 pi times 10 to the power negative 6 meters squared times the Young modulus of aluminium, which is Ea, is going to be 70 times 10 to the power 9 Newton per square meters. And if we work out here, we're going to see that Fs is going to be equal to 12 Fa. Sub equation 5 into our first equation, which is equation number 1, the equilibrium equation, and say Fa, right? Fa plus Fs, and Fs, we know that Fs is 12 Fa. That should give us F, and that means 13 Fa should give us 240 kilonewtons, and Fa will be equal to 240 over 13 kilonewtons. And for now, I'm going to leave it as a fraction so that I can obtain some exact values. So Fs is equal to 12. Fa is going to be 12 times 240 kilonewtons. And if we solve this, it's going to give us 2880 over 13 kilonewtons. Stress in the steel is going to be Fs divided by As, and that's the cross-sectional area of the steel. So Fs is 12880 divided by 13, but we have kilonewtons, and I'm going to change it to newtons by multiplying by 10 to the power 3. It's going to be newtons right here, and I'm going to divide this by the cross-sectional area. The cross-sectional area of the steel As is 100 pi times 10 to the power negative 6 meters squared. Okay, and if we do this, we're going to get 705,178,824.8, and I'm going to change this number, so it's Newton per square meter. I'm going to change it to something like mega. Okay, so we have these three numbers here and these three numbers here, so I think I can write this one as 005.18 mega Pascal. That is going to be the stress in the steel. And now I'm going to move on to stress in the aluminium, and this is going to be Fa, the force in the aluminium applied directly to the aluminium, and Aa, the cross-sectional area of the aluminium region. And you know the force Fa is 240 over 13 kilonewtons. We're going to change it to newtons. We're going to divide this by 25 pi, which is the cross-sectional area, times 10 to the power negative 6 meters. And if we do that, we're going to get 235,059,608.3 newtons per square meters. By changing it to megapascal, we're going to get 235.06 megapascal. And for part 2, we want to find the change in length of the assembly. So from here, we know these forces are compressing, so that means it's going to shorten. So if we look at our force displacement relationship, we know that it's going to happen. You know, the change in length of the aluminum and change in length of the steel is going to be the same. So that means to find the shortening length, you can just choose aluminum or you can choose steel. So let me just choose steel. So I'm going to write part 2 here. The change in length of the whole assembly As is going to be Fs length Ls and As cross-sectional area, and then modulus of the steel. Fs is 2880 newtons over 18, right? And I'm going to multiply this one by, okay, this was kilonewtons. Okay, so let me just change kilonewtons to newtons. I'm going to multiply by 10 to the power 3. And the length, so the length is 200 millimeters right here. So these are supposed to be 200 millimeters. So I'm going to change millimeters to meters. It's going to be 200 times 10 to the power negative 3 meters divided by area of the steel, which is 100 pi, times 10 to the power negative 6 meters squared, times 210, which is Es, modulus of the steel, times 10 to the power 9 Newton meter squared. You can even choose aluminium, and if you calculate here, this one can go with this one. You're going to see you're going to get 6.715988 times 10 to the power negative 4 meters. You can even change this to millimeters if you want. The next question, we're going to look on the change in length of this problem. when there's a temperature change. So stay tuned. Don't forget to subscribe.